Here's your video about binomial expansion. With binomial expansion, we're talking about taking some quantity that has two terms and raising it to some exponent. Let's go through a few quick examples, like a plus b to the first, that's just a plus b. A plus b squared, either we know a pattern for this expansion. For any binomial squared, we know that the result is three terms. It's a squared plus 2ab plus b squared, basically our first term squared. The middle term is 2 times the product of a and b, and the last term is b squared. Either we know this pattern, or you could just multiply a plus b times another a plus b. This will be a 2 by 2 multiplication. We could call it FOIL. A squared plus ab plus b squared, and we do have like terms here, 1ab plus 1ab, to give us the 2ab. Now what about a plus b to the third power? We don't usually memorize this pattern, but we are, in this context, actually going to begin to look at the patterns that we get out of a plus b to the third power. But for now, we could think about take a plus b to the second and multiply to it another a plus b. We'll do that over here in some space. A plus b times a squared plus 2ab plus b squared. First, I'll distribute this a to a squared and 2ab, and b squared gives these three terms. Then distribute the b, and I expect to see some like terms. I'll keep them lined up. So that would be an a squared b, a 2ab squared, and then b to the third. And when we combine our like terms, we end up with a cubed plus 3a squared b, the sum of these two terms right here, and then a 3ab squared, the sum of those two terms there, and lastly, b to the third. So let's talk about some of the patterns that we can see so far. First, let's look at the exponent of 3. We're taking a plus b to the third power, and we see that our first term is simply a to the third, and our last term is b to the third. And that's a pattern that we see with these other examples. A plus b to the second, it starts with a to the second and ends with b to the second. A plus b to the first starts with a to the first, ends with b to the first. We can maybe even see something about the number of terms. When our exponent is 1, we get back just those two terms in the binomial. When our exponent is 2, we get 3 terms. When the exponent is 3, we get a total of 4 terms. So whatever our exponent is, we can expect to see that many terms plus 1. Exponent of 3 gives us 4 terms. Let's look at some other patterns that we can see being established here. Our first term is a to the third, and let's just focus on the variable a in each of these other terms. Our next term has a to the second power. The next term has a alone. We know that's a to the first power. And our last term does not have a whatsoever. We could even think of it as being a to the power of 0 equals that coefficient of 1. So our terms have a with decreasing exponent, starting with the 3 that we see here and decreasing all the way down to 0, the last term that has no a at all. And let's look at what's going on with the b, which represents the second term in the binomial. We see b to the third all the way at the end. Our last term is b to the third. As we move back to the left, we see there's b to the second, and then b to the first. And no b from that first term, so that's like b to the 0, just like we had a to the 0 on the last term. So we see some clues about our exponent, and we know that each term appears with a decreasing exponent. The first term appears with a decreasing exponent left to right. The second term, the b, has more of an increasing exponent, or it's decreasing if we look at it from right to left. So we'll take these patterns that we see and try to establish more patterns for how we deal with these in the future. Now, if you're starting to look at the coefficients and saying, do we have a pattern here with our coefficients, where a plus b to the first gives us 1a plus 1b. A plus b squared, we know it starts with a squared, ends with b squared, and our coefficient in the middle is now a 2. And there's 1 and 1 with the a squared and b squared. A plus b to the third, again it starts with a 1a to the third and ends with 1b to the third, and we see our middle coefficients are both 3. Now, do we have a pattern here to say that the coefficients in the middle will always match up with our exponent? In fact, they don't, but let's take a look at one more example just to show that it's really not a pattern that we can use. We're going to multiply to come up with a plus b to the fourth. We have a couple options with what we've done so far. I could take the result from a plus b to the third and multiply that by another a plus b, or I could take the a plus b squared and multiply that to itself. That's a way to get a plus b to the fourth. Couple ways. I'll choose to go ahead and multiply this result of a plus b to the third by one more quantity, a plus b. Let's get some space to do this multiplication. I'll first take the a and distribute that to each of these four terms. Leaves us with these four terms. And then we'll distribute the b to each of these four terms. We do have like terms as expected, and when we combine our like terms, a to the fourth, there's a 4a to the third b, but in the middle we had to combine a 3a squared b squared with another 3a squared b squared to give us this 6a squared b squared. So definitely an exponent of 4 will not lead to all coefficients being 4. We can expect our first coefficient and last coefficient to be 1. The exponent that we see would be our next coefficient and the second to last coefficient, but there's something else going on with some of these other coefficients, like this 6 that we see here. So let's rewrite this back on that page we were just looking at to again see that we have patterns about a to the fourth is our first term, b to the fourth is the last term. That degree, or the exponent 4, does show up as our coefficient of the second term and the second to last, but we need to explore how we come up with this coefficient of 6, and we'd like to come up with a way that we can find that the coefficient is 6 without actually having to do all the multiplying that we just did. One option that we have for finding those coefficients would be to use Pascal's triangle. We're going to form a triangle with numbers. The way we will do it will be to start with a 1 at the top of this triangle. And we're looking at a couple of things. We're definitely forming a triangle, but each row after this 1 should have one more term. Our first top of the triangle is one term. The next row is going to have 2 terms. The next row will have 3 terms. We know the first and the last will be 1. It's in the middle where we're coming up with some of these different coefficients. So let's first come up with the 2 sides of the triangle that they are all 1s. Every row of this triangle starts and ends with a 1, just like how we saw our coefficients. The first coefficient was always a 1, the last coefficient was always a 1. These rows are going to show us our coefficients of that expanded polynomial. Now the way that we fill in these numbers in the middle of the triangle is to look at which 2 numbers are directly above it, up left and up right, and we add those 2 numbers together. So in the third row we should have 3 terms, starts with a 1, ends with a 1. In the middle we have to look at the 2 diagonals above it. We see a 1 plus 1, so we know in this spot we will use a 2. And now we see our coefficients of a plus b squared. 1a squared plus 2ab plus 1b squared. Now the next row should contain those coefficients 3 and 3. Let's use our pattern for filling in this triangle. In our spot here, we know this should have a total of 4 numbers. So our first spot here, we're looking diagonally above it is a 1 and a 2 added together equals 3. Over here, same thing. Above it we have a 2 and a 1 added together equals 3. So we have coefficients of a plus b to the third power. 1a to the third plus 3a squared b plus 3ab squared plus b to the third. Now let's remember some of the patterns that we saw earlier for when we get to some of our examples in the near future. We talked about, first of all, a had a decreasing exponent. Started with a to the third, the next term had a to the second, the next term had a to the first, the last term had no a at all. Then we look at the b's. The first term has no b, and now we're increasing our exponent. So the second term has b to the first, the next term has b to the second, the last term has b to the third. Lastly, we fill in our coefficients, And one way we find our coefficients is with this Pascal's triangle. Now, it's given the name Pascal's triangle in honor of a French mathematician named Blaise Pascal, but the truth is that this pattern was really found all over Europe and Asia independently of one another. So it gets named after Pascal, but we know there were many cultures at many different times in history who discovered this pattern. Well, let's go to our next row. This will have a total of 5 terms, and it is when we do a plus b to the 4th power. We saw a plus b to the 4th power had those coefficients 1, 4, 6, 4, 1. So do we see those numbers being revealed from the Pascal's triangle? Our first spot has directly above it a 1 and 3. Those things added together would equal 4. Our middle spot has above it 3 and 3, so we do get the 6. And this spot back here, diagonally above it, would be a 3 and a 1, for a total of 4. So the coefficients of a plus b to the 4th right there. Let's do one more for the coefficients of a plus b to the 5th. We should have 6 spots here. So our first spot right here would be below a 1 plus 4 to make 5. The next spot, 4 plus 6 to make 10. Here we have another 6 and 4 to make 10. And lastly, below a 4 and 1 to make 5. So here's a way for us to find coefficients, and we do see some symmetry, and as we go through the examples in the future, we'll point out where we can use the symmetry to our advantage. One thing to point out is about the degree, the exponent of our binomial. This is the 3rd row, and it has 3 terms, but this is from a plus b to the 2nd power. Our 4th row, which has 4 terms, is from a plus b to the 3rd power. So we want to be cautious when we use Pascal's triangle that if our exponent is, for example, 4, we're actually looking at the 5th row. And this, our 2nd row, would be a plus b to the 1st. We could see that as coefficients 1 and 1, 1a plus 1b. Here's a plus b to the power of 0. It equals exactly 1. So remember, a plus b to the 0 is our 1st row. A plus b to the 1st is our 2nd row, and so on. As we identify what exponent to use, we'll understand we need to add 1 to figure out which row of Pascal's triangle to use to find the coefficients. But frankly, I use the pattern that look at the exponent, and that tells me what my 2nd and 2nd to last coefficients should be. A plus b to the 5th, I'm looking for the row that starts with 1, 5 and ends with 5, 1. But we'll keep all of these ideas together as we proceed. We do have another option for coming up with these coefficients. Instead of producing a big triangle, let's talk about this approach. I'll clear some space, but keep these results here as things that we'll check up on with this new approach. Clear some space, and the way that we find the coefficients is with a binomial coefficient notation, which you may have seen before. In parentheses, just one number over another. Avoid using a fraction bar because we're not talking about a fraction per se as an n over k, but this notation means do in the numerator n factorial, in the denominator k factorial times n minus k factorial. And the exclamation point, the factorial, means whatever number we use, we multiply that number by all of the whole numbers that are less than it, down to 1. So 4 factorial, if n equals 4, a 4 factorial would be 4 times 3 times 2 times 1. That would be 24. A 5 factorial would be 5 times 4 times 3 times 2 times 1 equals 120. So quick reminder about what the exclamation point, the factorial notation, means. And the way we choose which numbers to use is as follows. N is our degree of the binomial expansion. So if we're talking about a plus b to the 4th, it means n equals 4. K stands for which term in the expanded polynomial are we looking for. But there's a quick caveat, a quick warning there, that when we talk about k should be which term, we have to actually subtract 1 because we want our first term to be when k equals 0. Our second term is when k equals 1 because we want the last term to match up with the degree. Meaning that if the last term is k equals 4, then here's k equals 3, k equals 2, k equals 1, k equals 0. We have to always start out thinking that that first term matches up with k equals 0, because whatever our degree is, we'll have one more term in our expanded polynomial. Degree 4, 5 terms. Degree 5, 6 terms. So keep that first term matching up with k equals 0. So to demonstrate, let's find these 5 coefficients here. Let's start with our first coefficient. Now we know it's 1, and as we go through examples, we'll just say, I know the first coefficient is 1, I know the last coefficient is 1, but just to demonstrate the use of this binomial coefficient notation. Our first term, we would represent this as n over k, 4 over 0, because our first term, k equals 0, here's nk for 0. Using the factorials that we have in this fraction here, we're doing 4 factorial over 0 factorial times 4 minus 0. That's just the 4 factorial. Now 0 factorial, if you're thinking, how do we manage this? Shouldn't it equal 0? Well, 0 factorial has its own special definition as equaling a positive 1. So we're left with 4 factorial, that's 24, over 1 times 24, basically a 24 over 24, the fraction that equals 1. So there's our coefficient 1, which we were expecting to see. What about the next coefficient? In the second term, that's when k equals 1. Our binomial coefficient notation is 4, 1. The fraction becomes 4 factorial over 1 factorial times 3 factorial. So 4 factorial is 24, 3 factorial is 6, 24 over 6 equals 4, and there's our next coefficient, 4. Let's hit a couple more. The third term, and k equals 2 on the third term. Binomial coefficient notation has 4, 2. Writing this fraction, 4 factorial over 2 factorial times another 2 factorial, this is 24 over 2 times 2, and it can be helpful that we write out the multiplications. Now I left off the 1s because anything times 1 equals itself, but here's the 4 factorial. 4 times 3 times 2, I left off the times 1. 2 factorial is basically 2 times 1, and another 2 times 1, so there they are. And writing out the numbers that we're multiplying, we can almost always see some nice canceling, nice simplifying to do. So 4, I'll wipe that out with the 2 2's in the denominator. We're left with 3 times 2 equals 6. Or you could just as easily say this is a 24 over 4 equals 6. But there is our next coefficient, the coefficient of the third term, 6. So that would be our other approach for finding coefficients of the expanded polynomial. Let's do one more for an example. Let's find this coefficient right here. It should be a 10. It is the 1, 2, 3. It is the fourth term, and our degree is 5. But if it's the fourth term, be cautious there. Fourth term means k equals 3. Here's our binomial coefficient notation, 5, 3. 5 factorial over 3 factorial times 2 factorial, still following this pattern that we see right here. It's basically our definition of the binomial coefficient notation. I'll write out these multiplications, 5 times 4 times 3 times 2 up in the numerator. In the denominator, right here is the 3 factorial, 3 times 2, and here is the 2 factorial. And do we see things that could be simplified? I'm going to wipe out the 3 with the 3, and we have options. I think I'll take the 2, 2 in the denominator and wipe that out with the 4 in the numerator, seeing it as like a 4 over 4. We're left with 5 times 2 equals 10, our coefficient right here that we were expecting to find. So there's our other approach for finding coefficients, and in the examples that we are about to do, we'll do a little bit of each. We'll do some where we use Pascal's triangle, and we'll do others where we use binomial coefficient notation, just to keep sharp on both ways. So let's begin to go through examples where we actually take a binomial and expand it using those patterns that we were just pointing out. We'll take for our first example x plus y to the sixth. I have a table that I like to use just to stay organized with these problems. What I need to know about this table is that it will always have three rows. A row for the coefficient, a row for the first term, what happens when we do x to some power, and a row for the second term. So coefficients up top, then our first term, and then the second term. When it comes to columns, I will need one column for each term of the expanded polynomial. Since our exponent is 6, we will have a total of 7 terms. Let's deal with the coefficients last and first fill in our terms. Let's deal with the x first. We know that the first term has x with our degree, this exponent 6, x to the sixth, and we decrease this exponent with each successive term. So I'm quickly filling in x to the fifth, x to the fourth, and so on, down to x to the first. The last term, x to the 0, I could just simplify that and call it 1. But don't forget that the last term is not having x to any power. It's because it's x to the power of 0, which equals 1. Moving on to the second term, which is a y, we know that it has its exponent increasing from left to right. So I'm starting with a 1. Then I have a 1, that's y to the 0. Here's y to the first, y to the second, y to the third, and so on. So I've pretty quickly found that the first term, the first part of each term, and the second part of each term. Now let's fill in the coefficients. Now we just went through making Pascal's triangle, but we'll go through it again from scratch. We start with a 1 in the first row and 1, 1 in the second row. Each row will always begin and end with a 1, but the numbers in the middle, we look at the two diagonally above it and add them together. So our next row should be a 1, 2, 1, and the 2 is from adding the two 1s right above it. The next row should have 1, 3, 3, 1. Next, 1, 4. Here's a 6 from the 3 plus 3, another 4 from the 3 plus 1, and we always end with a 1. Next row starts with a 1. Next number is below a 1 plus 4, so we have the 5. Next, below 4 plus 6 equals 10. Then another 6 plus 4 equals 10. Then a 4 plus 1 is 5. And end that row with another 1. Let's do the next row, starting with a 1. And then our next number is the 1 plus 5, 6. Then we have a 5 plus 10 to get 15. Here's a 10 plus 10 to get 20. Then we see our symmetry kicking in. Once we get halfway, we're going back to a 15, then to a 6, and ending with a 1. We always get these rows being symmetric. They begin and end the same way. 1, 6, 15, 20, 15, 6, 1. So there's the row that we want. It is the 7th row, but I was just on the lookout for once I hit a coefficient of 6, because we're dealing with a plus b, or x plus y, to the 6th power. So I'm looking for the row that goes 1 and then 6. So we've got it right here. I'm going to take all these coefficients and bring them back to the table. 1, 6, 15, 20, 15, 6, 1. Now lastly, each of these columns corresponds to a term of the expanded polynomial. I just need to multiply all these parts together. First term, 1 times x to the 6th times 1, that's just x to the 6th. Here we have 6 times x to the 5th times y, there's that term. And we're just proceeding along the way. Then 15x to the 4th y squared, 20x cubed y cubed, 15x squared y to the 4th, 6xy to the 5th, and lastly, 1 times y to the 6th is positive y to the 6th. So we have our 7 terms of the expanded polynomial. Let's continue with another interesting example, 2x minus 3y to the 4th. I'll set up the table. I have a column for coefficient and then first and second term, and columns for the 5 terms that we'll expect to see when we expand this binomial to the 4th power. Again, exponent is 4, a total of 5 terms. Now since we did just make a nice Pascal's triangle, I'll just go right back to it and find the row that has 5 coefficients. Right here, 1, 4, 6, 4, 1. So let's get those in the table, 1, 4, 6, 4, 1. Now when we deal with our first term and our second term, we have to be a little bit cautious here, because our first term in the binomial is actually 2x. So when we talk about what shows up in each of these terms, we have to think about the entire quantity 2x to the fourth power, then 2x to the third, 2x to the second, there's 2x to the first, and lastly 2x to the power of 0, which equals 1. And what I'll need to do now is a little bit of simplify. What is 2x, this entire quantity 2x to the fourth power? That's not just 2x to the fourth, it's 2 to the fourth times x to the fourth. So that is 16x to the fourth. I'm going to go through and simplify each of these the same way. This becomes 8x to the third. This becomes 4x squared. Okay, the coefficient as well as the variable are both raised to the power. So that gives us the 16x to the fourth, and so on. 8x to the third, 4x squared. Here was to the power of 1, so it's good as is, just a 2x. We'll leave this alone because it's an exponent of 0. So regardless of if it's x or 2x or 8x, anything to the power of 0 equals 1. We're going to have to handle the negative 3y in a similar way. I can't start off saying in the first term it's a 1, again, because it's that exponent 0. Now it's a minus 3y, so we're going to have to bring down a negative 3y as this part, our second term in the binomial. There's negative 3y to the first, negative 3y to the second, negative 3y to the third, and finishing up with negative 3y to the fourth. And a couple of these need some simplification. Negative 3 squared would be a positive 9y squared. Negative 3 to the third, so now we're back to a negative because our exponent is odd, so it's a negative result. Negative 3 to the third is negative 27, and there's the y to the third. And negative 3 to the fourth becomes a positive 81, and the y to the fourth is right there. So cautious about, once our terms have a couple of factors in there, we need to take the entire quantity and raise it to the exponent. And often what I'll do is write in the table, do the simplifying. Because once I have everything simplified, it's just a matter of multiply right down these columns. Our first column, 1 times 16x to the fourth times 1, that's just 16x to the fourth. Next, 4 times 8x cubed times a negative 3y. So the coefficient gives us a negative 96, and now we're bringing down x cubed and y to the first. Our next term, the coefficient would be 6 times 4 times 9, that's a 216, and then the x squared y squared. Next column has 4 times 2 times negative 27, that's a negative 216, and then the x to the first and y to the third. And lastly, 1 times 1 times 81y to the fourth. We don't see the coefficients of this expanded polynomial matching up with the coefficients we found in Pascal's triangle, but they're there. We just don't see them because now we have extra coefficients from the 2x and the negative 3y. I'll always take this approach using a table. At times we'll have to do a little bit of simplifying before we multiply down these columns, but we'll always multiply the numbers together for the coefficient and then piece together the variable parts, the x's and the y's. Let's hit just a couple of more examples to try to show all the ins and outs, the different types of problems we might see, but this approach that we've got going is exactly what we'll use for all these expansion problems. Here's our next example, x squared plus radical 2x, this entire quantity to the fifth power. I'm setting up a table, a row for the coefficients and the first and the second terms, and we need a total of 6 columns for an exponent of 5. Let's take care of the coefficients first. I'll just go back again to that Pascal's triangle we made. We're looking for the 6th row, the one that starts with 1, 5. Okay, 1, 5, 10, 10, 5, 1. Let's bring those back and put them in the table. Now, our terms in the binomial are a little bit complicated, so let's be cautious here. The first term will have x squared to the fifth, then x squared to the fourth, x squared to the third, x squared squared, x squared to the first, and ending with positive 1 for the x squared to the power of 0. Now let's fill in our second term that uses the radical 2x. I'll start on the right side this time and say back here is where we have the radical 2x to the fifth. Then moving left, radical 2x to the fourth, radical 2x to the third, and so on. First term is back to a 1 because of our exponent being 0. Now let's go through and simplify some of these a bit. Here we have power of a power. That's multiplying exponents. This becomes x to the 10th, then x to the 8th, x to the 6th, and so on, x to the 4th, x squared, and 1. Now let's simplify some of these radicals. The 1's okay, the radical 2x is okay. Here, the radical 2x squared, well, that's basically eliminating the radical. We're doing square root of 2x times another square root of 2x equals regular 2x. Radical 2x to the third, well, I could just think about taking my radical 2x squared, which came out to be just 2x, and multiplying that by another radical 2x. That's a good way for us to handle simplifying these radicals. So radical 2x to the third, a 2x times another radical 2x. Radical 2x to the fourth, that's basically this box right here times itself, squared. So we have a 2x times another 2x, 4x squared. And now in this box, we're just multiplying another radical 2x to this, so 4x squared times radical 2x. So everything has been simplified. Now let's multiply down these columns. The first term, x to the 10th. Next we have, now careful here, we're not intermingling the radicals with quantities that are outside of a radical. So we have 5x to the 8th times radical 2x. And this entire chunk is our second term from multiplying these three parts together. Next we have 10 times x to the 6th times 2x. Well, I see a 10 times 2 for a coefficient of 20, and then an x times another x to the 6th. So this is 20x to the 7th when we multiply these three parts together. Next, a 10 times x to the 4th times 2x radical 2x. Well, this 2x is outside of a radical. We can definitely multiply the 2 times the 10. We can multiply the x to the 4th times this x to the 1st, but the radical 2x is just tagging along. So this looks like a 20 x to the 5th with the radical 2x. Our next term, 5 times x squared times 4x squared. So this is a 20, and x squared multiplied together is x to the 4th. So there's a 20x to the 4th. And our last term, multiplying a couple of 1's to this 4x squared radical 2x. So there's our last term. A quick check that it's exponent of 5. We should have a total of 6 terms, which we do. 1, 2, 3, 4, 5, 6. We were cautious with making the table and doing the simplify, so there is our expanded polynomial. Let's hit another example, x plus 2 over x to the 6th. I'll set up a table, 7 columns for the 7 terms, and a row for coefficients for the first term and for the second term of the binomial. This time, let's use the binomial coefficient notation. So our exponent is 6. I know that each of these coefficient notation expressions here will have a 6 as the top number. The bottom number was our k value. So for the first term, k equals 0, and now we're increasing our value of k. So 6.1, 6.2, 6.3, 6.4, 6.5. Our last term should always be the same number in this binomial coefficient notation. So 6.6 looks good. Now let's evaluate these, but not all of them, because we know that first and last coefficients are 1. So let's not do more work than necessary. We know first coefficient is 1, last coefficient is 1. Since our degree is 6, we also know the second coefficient and the second to last coefficient will also be 6. Now let's just pretend that we don't remember exactly what these are from Pascal's triangle, just so we get practice with this notation. 6, 2. So this is a 6 factorial in the numerator. Denominator is 2 factorial times 4 factorial, because our number in the bottom here gets a factorial, and also the difference of these two numbers is another factorial in the denominator. So that 4 factorial comes from subtracting 6 minus 2. And when we evaluate this, we get 15. We know symmetry, so since I found this is a 15, I know back here this is also a 15. I'm not trying to do more work than I have to. Lastly, 6, 3. So this is a 6 factorial over 3 factorial times another 3 factorial, and that simplifies to equal 20. So we've got our coefficients in place. We used the binomial coefficient notation instead of Pascal's triangle, but both ways should give us the same results. Now let's deal with these terms. So our first term in the binomial is x. That's going to make life not too unpleasant right here. We're just going right down the line, x to the 6th, x to the 5th, to the 4th, and so on, down to x to the power of 0 equals 1. Now the next row is from a 2 over x, so I'll be a little bit more cautious here. I know it's going to start with a 1, and then we have 2 over x to the 1st, 2 over x to the 2nd. I'll keep that entire quantity in parentheses. And let's go ahead and do the simplify right now. 2 to the 2nd would be a 4 in the numerator, with x to the 2nd in the denominator, 4 over x squared. Next quantity, 2 over x to the 3rd, that becomes an 8 over x cubed. 2 over x to the 4th would be 16 over x to the 4th. 2 over x to the 5th, that's 32 over x to the 5th. And lastly, 2 over x to the 6th. 2 to the 6th, that's 64, so we have a 64 over x to the 6th. So everything has been simplified. We're ready to carefully multiply down each of these columns. And with this particular example, we're going to see some interesting simplifies that go on as we do these multiplications. So first, 1 times x to the 6th times 1, that's x to the 6th. Next, 6 times x to the 5th times 2 over x. Well, the 6 times 2 will give us 12, but x to the 5th over x, we can simplify that. It's just x to the 4th, 12x to the 4th. Same thing is going to happen here. We have a 15 times 4, a coefficient of 60, but the variables, an x4 divided by x squared, so that's 60x squared. And again, with variables, x4 is like in a numerator, but this x squared is in a denominator. And x fourth over x squared simplifies to equal x squared. Next, the 20 times 8 would be 160, but x cubed with a 1 over x cubed. That's wiped out completely. Our term right here is simply 160 with no variable part. Next column, 15 times 16, that will give us 240, and we have x squared over x to the 4th. Be cautious there. Our leftover x squared is actually in the denominator, so this next term is 240 over x squared. Think about if we have x squared over x to the 4th, simplify it to 1 over x squared, but the 15 times 16 gives us 240 over x squared. Next column, 6 times 32, that will be a 192. And then we have x over x to the 5th. That simplifies to be over x to the 4th. 192 over x to the 4th. And the last column, 1 times 64 over x to the 6th. That's our last term. So we've got a total of 7 terms, and these are the 7 terms of that expanded polynomial. Another example, just for fun, 1 plus radical 3 to the 4th plus 1 minus radical 3 to the 4th. Now there's no way for us to combine these yet. We have to do 2 separate expansions. So let's deal just with the first one. Exponent is 4, so we have 5 columns. I know about the coefficients, 1, 4, 6, 4, 1. In this row I have my first term 1, so I've got 1 to the 4th, 1 to the 3rd, 1 to the 2nd, 1 to the 1st, 1 to the power of 0 is still 1. Now let's go to the next radical 3. We have radical 3 to the power of 0, so we're starting with a 1. Then radical 3 to the 1st, radical 3 to the 2nd, to the 3rd, and to the 4th. Let's do a little bit of cleanup, especially on these radicals. Now, we know each of these powers of 1 equals just 1. We can clean up square root of 3 squared, that's just 3. Radical 3 to the 3rd, I'm just thinking about radical 3 to the 2nd times another radical 3. So I see 3 radical 3. radical 3 to the fourth, that's just 3 times 3 equals 9. So no special way of simplifying these radicals. You can do it any way you like. Some people like to say, well, let me just do 3 to the power of 4 equals 81, and then let me see if I can do a square root on that, and we could. Square root of 81 equals 9. You could look at this and say 3 to the third equals 27. How do I simplify radical 27? And we would get to a simplified answer of 3 radical 3. So we're using our old ways or whatever ways you prefer of simplifying radicals. There's nothing specific that we're doing to simplify these radicals in this type of a problem compared to what you've done in the past. Now that our table is simplified, let's take care of these columns. The first one, 1 times 1 times 1 equals 1. Next, 4 times 1 times radical 3. That's a positive 4 radical 3. Next, 6 times 1 times 3 is 18. 4 times 1 times 3 radical 3. We can multiply the 4 times this 3 outside the radical, but no other radicals to multiply to this 3 inside the radical. So we're looking at a 12 radical 3. And lastly, 1 times 1 times 9 equals 9. Now we do see some like terms we could combine. I could say 1 plus 18 plus 9 would be a 28, and these two terms would be a 16 radical 3. But I'm not going to go there just yet, because with this type of a problem, I know there's going to be some very explicit canceling that we will see. So I'm going to leave all these terms as is, and I'm going to try to do this expansion right now. But because it was so similar to 1 plus radical 3, I'm not going to wipe out all this work. I'm going to try to keep as much of it as I can. I know the coefficients will be exactly the same because it's still exponent of 4. Our first term is still a positive 1, so this entire row is unchanged. Our second row needs some adjusting because instead of a positive radical 3, we are using this time a negative radical 3. So I'm going to squeeze in here and make those changes. This column still uses a 1 because whether it's a positive radical 3 or a negative radical 3, once we do exponent of 0, it simplifies to equal exactly 1. But right here, this is now a negative radical 3. So that's going to make a change for when we do our multiplying of this column. Let's just move along and save all the multiplies for the end. Here, this is now a negative radical 3 squared. But a negative times negative is still positive. So this will actually stay as is, a positive 18. Negative radical 3 to the third. Now a negative with an odd exponent means the result is negative. And lastly, negative radical 3 to the fourth. Exponent is even, so we're going to come up with a positive result. The same thing that we have here, a positive 9. Below these 5 terms, I'll write what's going to be the 5 terms of this expansion of 1 minus radical 3. The first term is still 1 times 1 times 1 equals 1. Next, this is 4 times 1 times negative radical 3. So this next term is a negative 4 radical 3. Next term is all positive, still a positive 18. Here's another one where it becomes negative, a negative 12 radical 3. And lastly, it stayed the same because exponent was even, it led to another positive, so it stays a positive 9. Now what we're looking at is the two binomials expanded, but now we're interested in actually adding them together. And here's why I saved the combining like terms for now, because I can quickly see that the radical terms are getting wiped out. Positive 4 radical 3 with negative 4 radical 3. Here's a positive 12 radical 3 and negative 12 radical 3. Here we had all positives, so nothing's getting wiped out. We actually need to add all this stuff together, and it equals 56. One more type of problem I'd like to cover would be a problem like this. Find the 11th term of x plus 2 to the 15th. We're not going to do the whole expansion. I mean, I definitely could. It's exponent's 15, so it's pretty large. I would do a lot of work, and all I really have to do is just find the 11th term to answer this question. So we're going to use some of the patterns that we saw to come up with a quick way to find a specific term of an expansion. We know that each of these terms is made up of a coefficient and something that's a result of our first term multiplied to something that's a result of our second term. Now, how would we find the coefficient? If I don't want to do Pascal's triangle, I think the quickest way would be using the binomial coefficient notation. The degree is 15, so I know in this notation I'll have a 15 on top. But what do I want to have below for the 11th term? Remember, the first term uses k equals 0. The second term uses k equals 1. Whichever term I'm looking for, I have to take away 1 to find that value of k. So if I'm talking about the 11th term, take away 1 leaves us with k equals 10. Here's the expression that will give us the coefficient of the 11th term. Next, we're dealing with how is the first term handled. It's x to some power. Our first term uses x to the 15th, and then it decreases. So our second term uses x to the 14th, third term uses x to the 13th, fourth term uses x to the 12th, and so on. So counting that way, we'll find that the 11th term uses x to the 5th. We've counted down from 15 to 14 to 13, and so on, down to x to the 5th. Now our second term, the 2, has some exponent. The first term starts with 2 to the power of 0 and increases. So the second term is 2 to the first. The third term is 2 to the second. So following that pattern, we see that the 11th term will be using 2 to the 10th. Now we'll get to some sort of formula type expression that we could use, but let's just finish up with this example. 1510 in binomial coefficient notation. This is 15 factorial over 10 factorial times 5 factorial. Remember, the denominator includes this bottom number factorial as well as the difference of these numbers factorial. X to the 5th, that's pretty quick, x to the 5th. 2 to the 10th is 1024. Let's clean up our coefficient. This expression becomes 3003. And looking at what we are left with to multiply together, I can multiply the 3003 times 1024 for a big number, 3,075,072, and I'm bringing over the x to the 5th. So there's how we found the 11th term of this expansion. Now, to sum up a good way to remember how we can directly find these terms, I'm going to go back to our idea about k, because in all of the numbers that we see here, we don't see 11 show up at all, even though we're actually finding the 11th term. So we're going to use our value of k instead. When it's the 11th term, we subtract 1 to see that k equals 10. And then my quick formula for finding the coefficient would be nk, n always the degree, so it would be a 15, and k equals 10. Our next part, our first term in the binomial to the power of n minus k. We can see that it was a 5, and that's a result of subtracting n minus k. The second term in the binomial has an exponent of 10. It's actually matching up with k. So as we go forward, I'll understand that the coefficient will be nk. My first term in the binomial gets an exponent of n minus k. The second term in the binomial gets exponent of k. And the way I determine what my value of k is to see which term I'm interested in and then subtract 1. So let's do one more example to reinforce these steps. Find the 9th term of x squared minus 3y to the 13th. So we know our coefficient is nk. The next part will be our first term in the binomial, x squared raised to the power of n minus k. And lastly, we use the second term in the binomial. This time it's a negative 3y, and we use an exponent of k. So this is basically the formula that I'm thinking about. The coefficient nk, the first term in the binomial gets an exponent of n minus k, the second term in the binomial gets an exponent of k. Now n is our degree, n is 13. What is k? If we're talking about the 9th term, subtract 1 means k equals 8. Let's fill in these expressions. The coefficient is 13/8. Here we'll have x squared, and this subtract 13 minus 8 equals 5. And back here we'll have negative 3y to the k to the 8th. Let's do our factorials. 13 factorial over 5 factorial times 8 factorial. And this simplifies to equal 1,287. Let's simplify our next part here. X squared to the 5th is x to the 10th. And be cautious here, negative 3y to the 8th. So we're doing negative 3 to the 8th times y to the 8th. The negative 3 to the 8th becomes a positive 6,561, and there's the y to the 8th. Our last little bit of cleanup, multiply the coefficients, 1,287 times 6,561, and bring over the x to the 10th and the y to the 8th. So there is the 9th term of this expansion.